So this is one you might recognize. It's a kind of a reggae take by a band out of LA. Lighters.
Before we get into more of that, we should probably talk about technology. My name is Brett Young, and SmartMUD.io is our entry into the AEC Hackathon version 1.1. Here to tell us more about the problem we're trying to solve is Taylor Cupp.
Concrete gets hard.
When we were doing our planning for the hack, we wrote that down, and I didn't actually think that Taylor would record it, but I think we're better off for it. But why don't we try that again?
What's the problem? Concrete gets hard. And when it does so, it does it fairly quickly. Concrete operations on a project rely heavily on people, not so much on technology. When errors happen on projects and maybe a slab isn't poured flat, it's very costly to fix and remediate. That usually results in tearing concrete out, replacing the concrete. It's expensive, and it can really disrupt the flow of a project and the schedule of a project because it takes time.
Here's Jake Olson to tell us more about the problem.
For structures that include cast-in-place concrete, a concrete floor slab pour is typically one of the most expensive single-day operations on a job site. As construction tries to be more like manufacturing, our methods of quality control and quality assurance need to improve for these critical phases of construction activity. During a concrete pour, there are a large number of people in charge of quality assurance and quality control. But there is a significant lack of technology deployed to help with this quality. Compare this to a modern factory environment with statistical process control in place. There's sensors, control systems, and dashboards that are constantly managing the flow of production and providing valuable feedback loops for continuous improvement.
Here's Travis Voss to tell us about laser scanning.
More and more in the industry, we're seeing the precision that concrete has to be placed in going higher and higher. Super flat floors are used for many different applications. In hospitals, they're important because you have long corridors, and the aesthetics of a floor not being super flat could not look good. Additionally, manufacturing facilities rely on automated equipment that requires a super flat floor. These are just a few examples of areas that we're seeing this becoming more and more of a trend of having floors that go far above and beyond what we used to see in the industry. The concrete industry is nearly $50 billion in the United States. The problem that we're trying to solve here in ensuring that floors are flat and speeding up the measuring process on getting flat floors would have a huge impact across the industry, not only on Mortenson, but the industry as a whole.
Here's Travis Voss to tell us about laser scanning.
Yeah, hi, I'm Travis Voss. For this AEC Hackathon, I'm with the SmartMUD.io team. Just wanted to talk a minute about the scanner we used here. We use Hell Mechanical Scanner. We've had this for almost 2 years. It is a Faro Focus F70. Quick specs, it has about a 70 meter range, up to 976,000 points per second, with up to 1 millimeter accuracy.
For construction to be more like manufacturing, we need to deploy technology in our job site processes, starting with the most high-value operations, such as these slab pours. Our hack uses lasers, well, 3D laser scanners to be exact, which create point clouds, and a real-time analysis using open source tools to provide immediate feedback on a key quality metric, the flatness of the top of concrete. By providing this information real time, when contractors can still act on it and improve or remove defects in slab flatness, we significantly improve the contractor's ability to meet specifications up front and we reduce rework and delays. Today, the current state of the art is to validate flatness requirements after the concrete is placed and cured. This makes corrections and adjustments very expensive. The greater vision for this hack is that the information from multiple sensors is aggregated on the cloud. This digital twin for production control would be managed by the general contractor, supplemented by data from all subcontractors on the job site. The digital twin therefore becomes accountable to all project stakeholders.
We can talk about the actual hack and what we actually did. The architecture was that we'd have a laser scanner on a job site pointed at a concrete slab collecting data. You'd then have a mobile phone that would be telling it when to scan, and then a computer would be connected to the scanner and be pulling the large data files off of the scanner, large proprietary data files. And from there, we would process it locally and segment it down and limit the amount of data that we're actually capturing, and transfer it over to the Unity game environment running on a AR-enabled device. And the beauty of that is that the AR device with Unity can actually go through and do processing of the point cloud and colorize it and point out the defects using various types of shaders that that look at the geometry, look at the point cloud, and filter and colorize it out. And that's very different from how we're currently manipulating point clouds, because normally you have a computer, large computer kind of grinding through all the data. And what we've actually done is we created custom code running on top of Unity that is GPU powered rather than being desktop bound. And that's really cool. GPUs run Bitcoin, and they're very, very powerful. And moving to that paradigm is better architecture, we think, for being able to give you real-time data. We had planned to do a field demo, but we ran into a bit of a problem. It rained, and the pour got delayed. So we'll show you here a mock-up demo, but before that, we can finish up with Jake.